Hi, people. This is a follow-up to our discussion on two-source interference. I put a graphic up on the top here that says two-slit pattern. And you'll notice, hopefully it should remind you of what you saw today when we showed our two-source, our double-slit interference pattern from both our green and our red laser. And you'll notice that there are, it looks to me like right there is the central maximum. There's the first order max. Here's the second. Here's the third. But what happens here is things seem to dim out, but then come back, and I don't know what number maxima those are. But the double slit, the double slit physics and the double slit trigonometry and algebra and stuff doesn't account for why it goes. I don't know how well you can see this. I hope you can see it. Bright, dark, bright, dark. We don't have a way to account for that with just the double slit stuff. But what we do have to do is look not at what two slits do together, but at what a single slit does by itself. And there's something called what we've called diffraction and single slit diffraction. Right? Diffraction, if you remember, is the fact that when waves get to an obstacle, they can bend around it, or in this case, what we call an aperture or a slit, waves can do that when they go through it. They can spread out. All right. Well, with that in mind, we sort of have to remember something that we saw first when we started talking about refraction. When we talked about refraction, we showed a boundary between two media, and we had waves coming in like this, coming towards this boundary. And if you remember, in the applet that I used to demonstrate what I wanted to demonstrate, there were a bunch of points like this. And when a wave, like say when this wavefront, that wavefront, hit those points, remember they started doing boom, they all started doing their job and propagating more waves. Right? And there's a principle, an idea that says that's what, that's kind of the nature of how waves propagate, is that every place in space can act as sort of the source for new waves if they are excited or oscillated by a wave. So if a wave gets to you, your job is to propagate the wave. And every place in space can do that. And with that in mind, what we can do is look at the slit here, not just as a slit, but as literally an infinite number of places in space. Even though these slits can be really, really skinny, there are still an infinite number of places within that slit. And if we do this and divide the split in half, now I'm going to define the width of this slit by W. All right. So if we divide that slit in half and look at one location in space right there and one location in space right there, well, within this single slit, those two locations act like two sources for a two-source interference. All right? And furthermore, there are really an infinite number of other locations that are half a slit width apart. The green ones are half a slit width apart. The blue ones are half a slit width apart. The black ones are half a slit width apart. All right? And so if I take, the black ones, again, each one of those, waves from that might go like this, and waves from this might go like that. And we can do the same trigonometry / geometry that we did before and say, well, there's this angle theta that shows up right here also, and there's some little path length difference from each one of those places in space. And if that path length difference is, just like it was for two-source interference, if that path length difference is, what do you call it? Well, a wavelength or an integer number of wavelengths, then you can see constructive interference from those two sources. All right, so the only difference here is when we had two source interference from two slits separated by a distance d, we said that, well, d sine theta had to be equal to an integer number of wavelengths in order for us to experience or observe, what do you call it, constructive interference. Well, here, it's the same sort of thing, but, well, the distance between any of these two sources is half of the slit width. So W over 2 sine theta. If that's an integer number of wavelengths, whoa! Okay. You still recording? Oh, yeah. You're so lucky I wasn't swearing just now. I mean, typically I'd be mad at if I thought the recorder sounds. Anyway, yeah. So what we have here is, we can end up with, well, the same sort of approximations we can use if we want. If we call this L and we call the distance, from the central maximum, which would be like here, to the first order maximum, say, out here, we call that distance x. Well, remember we said that the tangent of theta is x over L, and if we approximate this as a real small angle, those two things are equal, and what we get is W over 2 times x over L is n lambda, right? Or if we want to look at the x for these, hang on a sec, and we'd say that x is, well, let's see, 2n L lambda over W. All right? And, well, that sort of is like the x. I wish I hadn't used x. Why don't I call this instead y? I'll call this y, and that y, and this y. Right, and so this says that, well, how far is it from central max to the first order maximum? Well, that depends on the width of the slit itself, not the separation between the slits. Okay? And if we assume that the slits are like even narrower than the separation between, say, two slits, well, then what we get is a pattern that looks something like this. People will draw these sometimes as like what's called an intensity clot, and it says that what you'll get is you'll get a big central maximum, and then outside of that you'll get dimmer, what do you call them, maxima, secondary and tertiary and stuff. All right? Now, within this, so that's really from, this is what we call a single slit diffraction pattern. Now, within that, what we can see is the double slit interference pattern that might look like this. We get something like this that does that, and this that does that, and this that does that. And these, really what we're almost showing is that mathematically the double slit intensity should just go like that. Bright, dark, bright, dark, bright, dark, bright, dark. But what it has to do is fit within the single slit envelope. And so even though it sort of says, the math says, well, we should have a bright spot, say here, the single slit envelope doesn't allow that to happen. And that's why we saw what we saw today, with sort of a big, well, that's why you see what you see here. You see this big area where there's a lot of bright, but within that bright, there's individual brights. The big, broad bright is a single slit diffraction pattern. And the little brights within them come from the two slits, the fact that there are two. Did a little looking around to try to explain why the single slit has a big intensity in the middle, and that intensity, even when this is a maximum, is lower out here. And it's, well, it's kind of way beyond what we talk about. All right, but what you should be able to, you know, I guess at least talk about. It's pretty rare that the AP asks about the location of minima and maxima for a single slit, but it's not out of the realm of possibility. But you ought to be able to, you ought to have in your mind that for a double slit interference pattern, the double slit pattern has to fit within what we call the single slit envelope. All right. So in red, right, is our double slit interference pattern. Like we said, it has to fit within the single slit diffraction envelope. Okay? And remember, for double slit stuff, we said d sine theta is n lambda, and the tangent of theta is, for us, x over L, right, where x is right there. And but for the single, there's what we call y. All right, so for this, we can say that for the small angle approximation, dx over L is n lambda. Let's see, so that means that x is going to be n L lambda over d. But if we imagine that the slit separation d is larger than the slit width w, well, that's when we get, well, a case it looks like we've drawn here, where the single slit has a much wider spread and the double slit has a, well, a narrower one. Okay? So, good to be able to talk about why we saw what we saw today. Okay, folks? All right. Adios.